title of my presentation is Combinatorial Interference Models in Wireless Networks. So here's the outline of my talk. First, I'll give a formulation of the main problem in wireless networks that we'll be solving. And this problem turns out to be a graph theoretic problem. It has to do with fractional chromatic number of graphs. And so I'll get to that here. It turns out that it's generally NP hard to solve this problem optimally, and we will be looking at efficient distributed solutions to this problem. If every node in the network has information only about its d-hop neighborhood, then what are the best kinds of decisions that can be made? So that's what we will be discussing. Those are called distance d-distributed algorithms. And then I'll be looking at the worst case performance of these algorithms. And it turns out, I mean, if we have time, we'll also look at how the interference can be modeled using hypergraphs rather than graphs. These are more general and more powerful interference models. And I'll conclude with some open problems and directions for further research. So consider a wireless network, which is modeled by a simple undirected graph G, where V is the vertex set, where every vertex is some wireless device. It could be a laptop, your smartphone, some Bluetooth device. And L is a set of wireless links. So anytime you have a pair of nodes which are within communication radius of each other, say you put a bunch of nodes in the Euclidean plane, and you join two nodes by an edge if and only if the distance between those two nodes is at most 1. So you have to decide in some manner which pairs of nodes are joined by an edge, and that's then you get your set L of wireless links. Now the problem is that nodes in the same neighborhood cannot transmit at the same time due to wireless interference. So they're all using the same frequency band, and therefore they must take turns transmitting. And which wireless links, which pairs of wireless links interfere with each other, that's modeled by a conflict graph, by the adjacency relationship in the conflict graph. So you have a conflict graph whose vertex set is L, which is the same as the set of links L in the network graph. And two links in the network graph, two edges in the network graph, or adjacent vertices in the conflict graph, if and only if they interfere with each other. Now, how exactly the adjacency relationship in the conflict graph is determined depends on the particular context. It depends on the application. We'll look at a couple of different ways to do that. And this notion of using conflict graphs to model the interference was proposed by Jane and his co-authors in 2003. Even earlier, the notion of conflict graph, it's a very general and fundamental idea, which was anytime you have a competition for resources, you have a graph coloring problem, and the graph that you're coloring is usually called a conflict graph because there's a conflict in terms of allocating resources to the vertices that are adjacent in that graph. So where we have two graphs here, a network graph G, whose links are the wireless links, and a conflict graph GC defined in that manner. So let's look at an example. So this here we have a network graph, and the graph is denoted G. V is a set of wireless nodes. So for example, right here you have a wireless node. Now what happens is that every node is equipped with only one transceiver. What that means is that this node here cannot both transmit on link A and link B at the same time. So if it transmits on A, it cannot receive or transmit on B because it is only equipped with one transceiver device. The transceiver is a transmitter receiver. So it's a word that's short for transceiver, for transmitter and receiver. So it can either transmit or receive on any one of the edges which are incident to it. That means that links A and D cannot be active at the same time. So in the conflict graph GC, we make them adjacent. Okay. Now another example would be if you take links, let's say A, E, and G. Now these three links can all be active at the same time. Okay, wireless transmission can take place simultaneously on all these three links because they share no endpoints in common because they form what's called a matching in this graph G. So here, when you construct the conflict graph, you can see that nodes A, E, and G have no edges between them. So basically, another way to say this is that the conflict graph GC is the line graph of the network graph G, where the line graph is defined to be the graph whose vertex set is a set of edges of the graph G, and two vertices are adjacent in the line graph if and only if the corresponding two edges in the network graph have an endpoint in common. So this model of interference arises in wireless communication systems, for example, in CDMA systems, when each node is equipped with only one transceiver. So here's another example of a conflict graph, which is the line graph of G. You have a Bluetooth network. You have a master node in, for example, your laptop, and you have several slave nodes in a Piconet. For example, it could be your wireless keyboard, your wireless mouse, your wireless headset, your wireless printer, and all of them transmit during different time slots, and therefore, in a Bluetooth network, these links here cannot be active at the same time. Therefore, they all interfere with each other, and when you construct the conflict graph, you get a complete graph on 4 vertices. Now, in this model of interference, where two edges are adjacent vertices in the conflict graph, is called the primary interference model, or sometimes it's called the one-hop interference model, because two links can be active at the same time if the distance between them in the network graph G is at least 1. There are other ways. There are many ways to construct the conflict graph GC. In IEEE 802.11 MAC protocol-based networks, you have what's called the secondary interference model. Here, you can when node A transmits to node B sends an acknowledgement back to node A. That acknowledgement is also received by node B, and therefore B cannot receive from E at the same time that A is transmitting to B. So when the communication between A and D takes place, when the communication along this link L1 takes place, L3 cannot be active at that same time. So in the conflict graph, L1 and L3 are actually adjacent vertices. On the other hand, L1 and L4 are far enough that there is no edge between them because they don't interfere with each other. So in this particular example of the secondary interference model, the way the conflict graph is constructed is you put an edge between two vertices if and only if the corresponding two links in the network graph are at a distance of at least 2. So the distance between the edge AB and the edge EF is 2 because there's 2 edges between those 2 edges. So in most of the next few slides, I'll be focusing on the primary interference model, where 2 links are adjacent vertices in the conflict graph if and only if they're incident to a common node. So L1 and L2 would be adjacent vertices in the conflict graph, but L1 and L3 would not be adjacent vertices in the conflict graph. That's because in the next few slides, it's different from this slide. In the next few slides, I'm going to be focusing on the primary interference model. Okay, so here's the problem of quality of service issues in wireless networks, where you're given a graph G. So here's the problem that you want to solve. You're given a few things, and you want to determine a yes or no answer to some question. And so here's the problem. You're given a network graph G where V is a set of vertices and L is a set of links. And the quality of service requirements are specified in terms of the minimum bandwidth required by each link. So node A might want to transmit to node B at a data rate of 2 megabits per second. So that's 2 megabits per second. So F of L is the data rate requirement for link L. And so F of L would be 2 megabits per second if L is that link AB. So every link has a data rate requirement. And if that link could transmit at full blast, it can transmit at a data rate of C bits per second. That's the total bandwidth of the shared wireless medium. And you're given also the conflict graph, which tells you which pairs of links interfere with each other. So given the network graph G, given the conflict graph GC, given the data rate requirement for every link, and given, you can convert the data rate requirement to the fraction tau of L of every unit of time that the link L wants to be active. For example, if a link L has a data rate requirement of 2 megabits per second, and if the shared medium has a total bandwidth of 4 megabits per second, then it's enough to say that the link L has a data rate requirement, that for link L, tau of L is 2/4, which is 1/2. As long as link L can transmit for 50% of every unit of time, it would achieve its data rate requirements. So given that, the question is determine whether the given set of flow rates is feasible or not. If the answer is yes, then you're able to satisfy the demands of all those links. Otherwise, you're not able to satisfy the demands and you reject their request and you deny them admission. So this is the flow admission control problem in wireless networks. So let's look at a very concrete example. So this is what you're given. This is your input for the problem. It's this edge-weighted graph. And the question is, can you satisfy the demands of all these links? So what you're given is a wireless network with 6 vertices and 6 links, 6 wireless links. This link has a data rate requirement of 0.1c bits per second. This link, L1, has a data rate requirement of 0.4c bits per second. L2 has a data rate requirement of 0.4c bits per second. Now, the total bandwidth of the shared wireless medium is c bits per second. So all these quantities here, all the demands for the links are less than c. So it appears that all the links can just transmit at c bits per second and achieve their data rate of 0.4c bits per second or 0.1c bits per second. The problem is that we're given that interference is modeled as the primary interference model, which means L1 and L2 interfere with each other because they share an endpoint in common. Okay, basically B has only one transceiver, so L1 and L2 cannot transmit at the same time. Well, that's okay because 0.4c plus 0.4c is still less than equal to c. So as long as you give you schedule L1 and L2 at different time slots, they can both achieve their data rate. So the question is, can you satisfy all these demands? And since this is a 5 cycle, the problem is not entirely trivial. It's not enough to check that the sum of the requirements of the links incident to any node is at most c. You need to do a little bit more than that. But here is actually the reason that here's a proof that the answer to this question is a yes. You partition your time axis into time slots, and in every time slot, which is 1 unit of time, that 1 unit of time could be 1 millisecond, 1 second, 1 microsecond, 20 milliseconds. But basically, in every unit of time, you partition it into 5 time slots. In the first time slot, both L1 and L3 will transmit. Each one of them will transmit at full blast at c bits per second. And that's not a problem because L1 and L3 is a matching. L1, L3 is a matching in this graph. And therefore, L1 and L3 is a set of links that can be simultaneously active. And so here's a schedule. In the second 20% of every unit of time, links L2 and L4 would be active. So you basically sort of rotate L1 and L3 by 1 unit, and you get a schedule. And then you can schedule L6 at the same time as you schedule L1 and L4 because L1, L4, and L6, let me just draw them here. Here's L1, here's L4, and here's L6. These 3 links can be simultaneously active under the primary interference model because they form a matching in the graph. And what you see here then is that L1 was active for 20%, and during that 20%, it transmitted at c bits per second. When L1 was active here, it transmitted at c bits per second. So it achieved in every unit of time a data rate of, 20 plus 20 is 40% of c, which is 0.4c. And therefore, the demand that link L1 had, that it wanted to achieve a data rate of 0.4c bits per second, was satisfied. And you can verify that the schedule satisfies the demands of all the 6 links. So the answer to the question, are these flow rates feasible? is yes, they are feasible. In fact, here's a schedule which achieves those data rates, which satisfies those demands. Now, we can simplify the notation a little bit. Since we're going to be, we can divide every one of the data rates by C, and instead of 0.4C, you can just have 0.4. And so what you would be specifying is the fraction of every unit of time that the link L demands to be active. And so here's a new simplified version of the problem where we got rid of the constant C. And that fraction 0.4 is tau of L1. So tau of L for every link L is the fraction of time that link L demands to be active. Okay? It's the fraction of every unit of time that link L demands to be active. So the input for your algorithmic problem is this edge-weighted graph. And you're also assuming that it's a primary interference model, which means that you want to know whether these demands can be satisfied. Is it possible that L1 can be active for 40% of the time, L2 for 40% of the time, L6 for 10% of the time, and so on? And at the same time, L1 and L2 cannot be active at the same time. L2, L3, and L6, no two of those three links can be active at the same time, and so on. And the answer is yes, you can satisfy those demands. Here is a feasible schedule. So it turns out that, it's not enough to just check. If you want to know whether, for example, here's an example where L1 wants to be active for 50% of the time, and L2 wants to be active for 50% of the time. Under the primary interference model, where the conflict graph is the line graph of the network graph, L1 and L2 interfere with each other. So even though L1 and L2 interfere with each other, the sum of their demands is less than equal to 1. So if L1 wants to be active for 50% of the time, and L2 wants to be active for 50% of the time, it appears you can satisfy those requirements because only two links interfere with each other, like L1 and L2 or L2 and L3. And together, the amount of time they want to be active is at most 100%. But it turns out the problem is trickier than that. And this example shows that it's not enough to just check whether the fraction of all the times, if you take all the edge weights, if you take the sum of all the edge weights incident to a vertex, and that sum is at most 1 for every vertex, that still is not sufficient for the given set of demands to be feasible, because it turns out that the fractional chromatic index of this graph here is more than 1. So we can formulate the admission control problem using the following terminology. You're given a network graph G and a conflict graph GC, whose vertex set L is a set of links of the network graph. You're also given a link demand vector where tau of L denotes the fraction of every unit of time that link L has to be transmitting for, or link L has to be active for. And the reason you're given the conflict graph is you need to make sure that adjacent vertices in the conflict graph, because they correspond to links that interfere with each other, must be active at disjoint time slots. Let I of GC denote the set of all independent sets of the conflict graph. So you know that the set of links that can be simultaneously active is an independent set in the conflict graph. So let I of GC denote the set of all independent sets of the conflict graph. A schedule assigns to every independent set I the duration of time that that independent set would be active. So T of I is the fraction of every unit of time that the independent set I would be active for. Now, the total duration then that a link I is active is basically the sum of the durations of all the independent sets which contain the link L. And once you come up with such a schedule, the total duration of the schedule is the sum of the durations of all the independent sets. And a demand vector tau is feasible if there exists a schedule of duration at most 1 such that in that schedule, each link L is active for duration at least tau of L. So going back to this example, these demands, 0.4 for link 1, 0.4 for link L2, 0.1 for link L6, these demands are feasible because you have a schedule of duration at most 1 such that, and the schedule maps the independent set L1 and L3 of the conflict graph, assigns to that independent set the duration 0.2, that's the fraction of time that L1, L3 would be active. So you assign to this independent set L1, L3 the real number 0.2. This independent set is assigned the real number 0.2. This one is this independent set 0.2, this independent set 0.2, and this independent set 0.2. All the other independent sets are assigned the time duration 0, and the sum of all the time durations assigned to all the independent sets is at most 1, and therefore we have shown that these demands are feasible because we found a schedule of duration at most 1 which satisfies all these demands. The admission control problem is, given the network graph G, the conflict graph GC, and a link demand vector tau, determine whether tau is feasible. Now, actually, to solve this problem, you only need the conflict graph GC. If you know the interference model, for example, if you know that it's primary interference, then you know that GC is the line graph of G. But so you don't have to be given G if you're given GC. So this extra information G is extraneous information, but in many problems, GC is obtained from G in a very particular manner. For example, under the primary interference model, GC is the line graph of G. Well, in that case, it's convenient to express your results and do your analysis on the network graph G itself. Sort of like if you want to color the edges of the graph, you might want to work with the graph itself and color its edges, rather than color the vertices of the line graph, right? The conflict graph would be the line graph, and instead of coloring the vertices of the line graph, you might want to just color the edges of the graph itself. So the independent set polytope, Pi, of a conflict graph is defined to be the convex hull of the characteristic vectors of the independent sets of the conflict graph. So basically, if you look at this more carefully, I'll share these slides later with the organizer, and you can also look at my papers if some of this terminology is not clear. But basically, it turns out that when you take this convex hull of all the characteristic vectors of all the independent sets, what you get is exactly the set of all link demand vectors tau which are feasible, meaning that which are feasible within 1 unit of time. Now, what I want to just tell you is that mathematically, the question of whether tau is feasible is equivalent, as I have mentioned here, to determining whether tau lies in the independent set polytope of the conflict graph. And it turns out that that's also equivalent to determining whether the fractional chromatic index of, well, I shouldn't say index yet, that's for a special case. It's equal to determining whether the fractional chromatic number of the vertex weighted conflict graph GC tau is at most 1. So what is that quantity there? Let me just quickly define it. So if B is the vertex independent set incidence matrix of the conflict graph, then you can look at this linear program, minimize one transpose. So that means so B is a 0-1 matrix where the ith vertex, if the ith vertex is in the jth independent set, then the ijth element of the matrix B is 1, otherwise it's 0. So that's how the matrix B is constructed. And so if you want to minimize one transpose, if you minimize one transpose X subject to Bx being at least tau and X being at least 0, if you actually make tau to be the all once vector, so there's a special case where you get the chromatic number of the weighted graph. So if you make tau to be an integer valued vector, and you put the additional constraint that x must be integer valued, then the value of the linear program is actually the chromatic number. And when you drop the constraint that x must be integer valued, you get the fractional chromatic number. And because you've dropped the constraint that x has to be integral, your feasible set is larger, and so your minimum is smaller. So the fractional chromatic number is always less than or equal to the chromatic number. And determining whether tau is feasible is equivalent to determining whether the fractional chromatic number of the graph is less than or equal to 1. So what that means is that if you look at the conflict graph of this graph, which is a 5-cycle graph, you want to know, and the vertices of those vertices of the conflict graph have a certain weight, which is the same as the weights of these links. So you take this edge-weighted network graph, and you form the vertex-weighted conflict graph, and you ask the question, is the fractional chromatic number of that vertex-weighted conflict graph less than or equal to 1? In this case, it isn't. So these set of demands are not feasible. But basically, you want to know whether that's less than or equal to 1. That's basically the problem we're looking at. So we're looking at a problem in fractional graph theory where you're given a graph, every vertex has a weight, and you want to know whether the fractional chromatic number of that weighted graph is less than or equal to 1. If it is, then the quality of service requirements of all those wireless links can be satisfied. Otherwise, they can't be satisfied. So that's the yes-no problem that we want to solve. Now, it turns out that that's actually an NP-hard problem. So the problem of determining whether the fractional chromatic number of a graph is less than or equal to 1 is NP-hard. In fact, even if you remove the weights, if you restrict all the weights to be 1, so you have an unweighted graph, just a regular graph, and you want to know its fractional chromatic number, it turns out to be NP-hard to calculate that as well. Now, in the next few slides, though, we're going to be looking at a special case where GC actually is the line graph of G. So we discussed this primary interference model where two links in the network graph G are adjacent vertices in the conflict graph if and only if the two links share a common endpoint. So in that case, the conflict graph is the line graph of G. If GC is the line graph of G, then the fractional chromatic number of the conflict graph is sometimes called the fractional chromatic index of the graph. Okay, sort of like saying that the vertex coloring number, right, the chromatic number of the conflict graph, if the conflict graph is the line graph of G, then you know that the chromatic number of the line graph is the same as the chromatic index of the graph itself. So similarly, the fractional chromatic index, the fractional chromatic number of the conflict graph is the same as the fractional chromatic index of the network graph G. Now, even though so it turns out that you can actually compute the fractional chromatic index of an edge-weighted graph G in polynomial time. That's kind of a very interesting result. So even though it's NP hard to compute the chromatic number of a graph, it's NP hard to compute the fractional chromatic number of a graph, it's NP hard to compute the chromatic index of a graph. The chromatic index is the edge coloring number. It's NP hard to compute that as well. It's actually possible to compute the fractional chromatic index of a graph in polynomial time. So it looks like we're done with the problem, right? We're done because our goal was to determine whether the chromatic number of the conflict graph is at most 1. And we can even assume that the conflict graph is the line graph of G. So we can make that assumption. So it looks like we're done because we've solved this problem in polynomial time. The problem is that you need to know the entire graph to make that decision. I mean, to find the fractional chromatic index of a graph, or for that matter, the chromatic index or the chromatic number of a graph, you need to know the entire graph. And in many practical applications, it turns out that the entire graph topology is not known at any single node. Each node in the network only knows about its local neighborhood. So a particular node A might know who are all its neighbors. That's all. It might not actually know who are, which vertices are distanced to from it. Because communicating the entire global topology and the demands of all the links to one center node is very expensive. So the communication cost means when a node transmits information to its neighbors and then about itself and its neighbors, and then those neighbors transmit it further down the road to their neighbors, and eventually all that information reaches a center node. That center node finally has the entire topology with it, but all that communication used a lot of battery power. And in many practical applications, battery power is limited. I mean, the lifetime of a sensor network depends on the energy consumption. And also, once that all that information reaches a center node, it's solving that centralized optimization problem is very computationally expensive. I mean, sometimes it's polynomial time, but for other confluent graphs besides line graphs, it's going to be NP hard. So we want to look at distributed solutions to this problem, distributed algorithms, where somehow we answer this question in a distributed manner. We'll look at exactly how, so we're looking at, so the thing is, we basically want to answer the question, is the fractional chromatic index of an edge-weighted graph less than equal to 1 or not? But we want to do it somehow in a distributed manner. So here's the main question. If each node has information up to only d hops away, a hop is the same as, an edge. So if every node only knows about the ball of radius d centered at the node, it only knows that subgraph, what are the best decisions the nodes can make? So the nodes have to somehow answer this question of whether the fractional chromatic index of the entire global topology is less than or equal to 1 by only looking at its d hop neighborhood. So so the thing is, we'll look at that, but let me first define the worst case performance of a sufficient condition. So we'll prove theorems that say that, the following condition S is a sufficient condition for tau to be feasible, meaning that if tau satisfies some conditions, then the fractional chromatic index of that edge-weighted graph is less than or equal to 1. Now, it turns out that the set of linked demand vectors tau, which satisfy the condition S, is not exactly the same as the independent set polytope, because S is only a sufficient condition, not a necessary and sufficient condition for feasibility. And but if you scale this set PS by some factor alpha, then it actually ends up containing the independent set polytope. And the smallest amount by which you need to scale the set PS so that it ends up containing the independent set polytope is what is defined to be the worst case performance of the sufficient condition S. So in the context of wireless networks, it turns out that this condition, this factor alpha determines how much resources are wasted. So if you have a certain amount of bandwidth, let's say 4 megabits per second, that you've paid for to use, you want to make sure you're using all of that efficiently. And this factor alpha can be interpreted as being somehow so 4 megabits per second might be enough in many situations, but you might end up concluding that it's not enough. And the scaling factor, which determines how much you wasted the resources, is what this factor alpha is. And that's why the worst case performance of these sufficient conditions is an important factor. You want to make sure that whatever network resources are given to you, that you use them efficiently, and you might not. And so you have to determine how bad your distributed algorithm is when compared to an optimal centralized algorithm. So I'm going to be discussing next some distributed algorithms for this problem, and there's something called a distance B distributed algorithm. So if this is your graph of your network, then when let's look at node A. Okay, so we have node A right here. And let's look at the one-hop neighborhood centered at node A. That means you take all the vertices whose distance to node A is less than or equal to 1, and you take the subgraph of the graph G induced by those vertices, and you get this graph. So this graph is the one-hop neighborhood centered at node A. Okay, so this is your graph G. The one-hop neighborhood subgraph of G centered at node A is this subgraph. The two-hop neighborhood, okay, the two-hop neighborhood subgraph of this graph centered at node A is this graph, because you take all the vertices in the graph G whose distance to node A is less than or equal to 2, that would be B, C, E, and D, and you take all the edges which are between those vertices, so L3 would be included in the two-hop neighborhood subgraph, and you take the demands of all those links as well, and so this is the two-hop neighborhood subgraph. Now, a distance one distributed algorithm executed at node A has to make decisions only based on this much information. It has the subgraph, it has the demands of all those links in that subgraph, and based on that, it needs to make a decision. A distance 2 distributed algorithm executed at node A has to make a decision based on only this much information. It would not know about this link L6. And a distance 3 distributed algorithm at node A would actually know about the entire graph, entire global topology, because the value of D chosen is 3, and that's the diameter of the network. So every node will execute a distance D distributed algorithm. And if every node executes a distance D distributed algorithm, and D actually happens to be less than the diameter, it turns out that you can actually still say some very interesting things. And that's what we'll talk about next. So here's the problem we're going to look at. Suppose that G is the network graph, and under the primary interference model, you know that the conflict graph GC is the line graph L of G. So given G, given a link demand vector where tau of L represents the fraction of every unit of time that link L has to be active for, determine whether the fractional chromatic index of that edge-weighted graph is less than or equal to 1. So that's the problem that we're going to be solving. And the issue is each node has only localized information. So instead of being given the edge-weighted graph, the entire edge-weighted graph G comma tau, each node only knows about the D-hop neighborhood. So G V sub D, G sub V comma D is the subgraph of the graph G, consisting of all nodes whose distance to V is at most D. So this is the D-hop neighborhood subgraph of G centered at node V. So node V only has that subgraph and the demands of all the links in that subgraph. And I'm going to skip a bit here. Yeah, okay, so it turns out that Shannon in 1949 came up with an upper bound of the chromatic index of multigraphs. So a multigraph is just a graph with parallel edges. Okay, and we don't have to worry about loops. We don't have loops. So you just have a graph with parallel edges, and the edge coloring number of a multigraph is at most 1.5 times the maximum degree of a vertex. This was proved by Shannon in 1949, and because of that, one can actually go ahead and obtain a sufficient condition for the fractional chromatic index to be less than or equal to 1. If basically, if you define the degree of tau at a vertex V in the network graph to be the sum of the demands of all the links which are incident to vertex V, then tau is feasible if the degree of tau at every vertex is at most 2/3. So this is basically saying that if you're given a graph, if you're given, for example, here, if this 0.4 plus 0.4 is 0.8, which unfortunately is not less than equal to 2/3. 0.8 is larger than 2/3. But if you, and similarly here, 0.4 plus 0.4 plus 0.1 is 0.9, which is again larger than 2/3. But if the degree of every vertex is less than or equal to 2/3, then yes, you can satisfy all these demands and the fractional chromatic index is less than or equal to 1. That's what this theorem actually here says. And sometimes, even like in this case, these demands are actually feasible, but the degree of this vertex is not less than or equal to 2/3. So we're only looking at sufficient conditions for tau to be feasible. So the fact that the degree of every vertex must be at most 2/3 is only a sufficient condition, not a necessary condition for tau to be feasible. And so it's a suboptimal, it's not both necessary and sufficient, it's suboptimal. And the factor by which such a decision can waste the network resources or be too conservative and reject demands which are still feasible is the factor of 1.5. Now, another sort of distributed algorithm is to look at is the following. I'll soon get to my results from 2020. I'll come up to that in a couple of minutes. But this was an earlier result from 2009. And basically it says if you have a graph G and a link demand vector tau, as usual, define the degree of a vertex to be the sum of the degrees of all the links which are incident to that vertex, some of the demands of all the links which are incident to that vertex. Then tau is feasible if the degree of tau at each vertex is at most 0.8, and the sum of the demands of the links in every triangle in G is at most 0.8. So going back to this example, the degree of this vertex is at most 0.8, but actually the degree of this vertex is not at most 0.8. So actually the condition that I just showed you would actually reject these set of demands and say that these are infeasible, even though they really are feasible. Okay, but it would actually, if this was given to you, it would know the theorem says that these set of demands are feasible. So there's a theorem that says that since the degree of every vertex is at most 0.8, these demands are feasible. So you know these are feasible by just looking at the degree of every vertex. So sometimes, okay, so anyways, let me get back here. The proof of this result used something called the imperfection ratio of the line graph of a graph being at most 1.25. This was proved by Gurke and McDiarmid in their Journal of Combinatorial Theory paper in 2001. So the imperfection ratio of a graph GC is defined to be, it's a graph invariant. Just like the chromatic number of a graph is a graph invariant, you can define the imperfection ratio for any graph, and it's the supremum over all non-zero link demand vectors tau of the ratio of the fractional chromatic number of the vertex weighted conflict graph to the clique number of the vertex weighted conflict graph. So given a vertex weighted conflict graph GC comma tau, you can find the maximum size of a weighted clique and find its fractional chromatic number, take their ratio, and then in the worst case, how far away can the correct value be from an estimate? And that ratio is the imperfection ratio. The reason it's called imperfection, okay, is because if a graph is perfect, then the imperfection ratio is 1. So you can show that if a graph is perfect, then the clique number and the chromatic number of this weighted graph are both equal. And the fractional chromatic number is a value that's usually in between the clique and the chromatic number, right? I mean, the fractional chromatic number is less than equal to the chromatic number, but always at least as large as the clique number. But since the clique and the chromatic numbers are equal, so are the clique and the fractional chromatic numbers. So this ratio is always 1, and you can show that this ratio is, that this imperfection ratio is larger than 1 if and only if the graph is not perfect. That's why it's called the imperfection ratio. And the intuition for how this quantity enters the picture is that in a distributed algorithm, every node has information about its neighborhood, So, if a node has, if a node only looks at its local neighborhood, okay, so let's say that you're looking at the one-hop neighborhood centered at node A, just this graph here, then if you look at all the cliques in the graph, they would be basically any clique in the graph, any clique containing A would be a part of its one-hop neighborhood subgraph. So the one-hop neighborhood subgraph centered at A would contain all the cliques and all the triangles. And so all the cliques are taken into account when you're computing this estimate, and the estimate of the fractional chromatic index. On the other hand, what you really want is a fractional chromatic index of the entire graph. And by only looking at all the cliques, you're basically missing out on the odd cycles. So it turns out that the imperfection ratio is determined by the odd cycles, and you can show that if the so I'll get to that soon, but you can basically show that the bottleneck in the performance of these distributed algorithms is the odd cycles. Okay, so here's the theorem. Basically, you have a network graph G. You have the you have the ith layer. The set of vertices whose distance to a vertex V is exactly I. That's the ith layer in the distance partition of the graph with respect to vertex V. Then you look at the ball of radius B centered at V. That's a set of vertices, the vertex V itself, all its neighbors, and so on until you get all the vertices whose distance to B is exactly V. And the union of all those vertices is called the ball of radius B centered at V. Now you take the subgraph of G induced by that ball, and you get the distance D neighborhood of G centered at V. Then you find the fractional chromatic index of that particular edge-weighted subgraph. That's the minimum duration of a schedule satisfying the demands of all the links in that subgraph. And the theorem says that given G, under the primary interference model, a sufficient condition for tau to be feasible is that the fractional chromatic index of that edge-weighted subgraph is less than or equal to 2D plus 2 over 2D plus 3, and for every vertex V. So basically, if every vertex V knew only about its d-hop neighborhood, and it computed the value for its d-hop neighborhood to be less than or equal to some quantity, then you can conclude that tau is feasible. So this is a sufficient condition for tau to be feasible. And you can actually implement that sufficient condition in pseudocode format, in the form of an algorithm. You can look at my paper, which was published in February in the IEEE ACM Transactions on Networking, where the details are given. I'm going to now go to another interesting problem, which is a generalization of the greedy algorithm for weighted graphs. So you all know the result that if you have a conflict graph GC and you want to color the conflict graph, the chromatic number of the conflict graph is less than or equal to 1 plus the maximum degree of a vertex. Right? It's 1 plus delta. So the chromatic number is at most 1 plus delta. That's a well-known result, and you can prove it by doing a greedy coloring of the vertices of a graph. You order the vertices in any manner, and you assign to every vertex a color which has not been assigned to, you assign to any vertex the smallest color, the smallest integer, the smallest positive integer, which has not been assigned to any of its neighbors. Now, you can generalize that and say if every vertex wants tau of L colors, where tau of L is it can be a fractional value, it can be any rational number, then it turns out that K colors are sufficient if tau of L, tau of a vertex plus tau of all its neighbors is less than or equal to K. So this result here, which is a sufficient condition for tau to be feasible, is really just a generalization of the greedy coloring algorithm for graphs to the case where the weights are allowed to be fractional rather than just integers. The induced star, now the question is, how good is the sufficient condition compared to an optimal condition, where if you actually knew the fractional chromatic number of GC comma tau, you can make a better decision. And it turns out that the performance is determined by the induced star number. So the induced star number of a graph G is basically, what you do is for every vertex V in the graph, you look at all its neighbors, gamma of V. You look at the subgraph of G induced by those neighbors. And then you take the maximum independent set, so the size of the maximum independent set in that induced subgraph. That's basically the number of leaf vertices in the largest induced star subgraph of G. That quantity is called the induced star number of G. And one can prove, okay, that the performance of the distributed algorithm that's given here is equal to that particular graph invariant. And that's the theorem that's there in this paper, that the supremum over all the tau of the upper bound to the fractional chromatic number determined by the greedy algorithm, the actual value is exactly equal to that particular graph invariant, sigma of GC. So it turns out that there are various ways in which you can construct the conflict graph. We looked at the primary interference model. There's something called the protocol interference model. Again, you can look at my paper, my publication, which is on my website, to go over this in more detail. I want to basically spend a few minutes on some open problems, so I'm going to skip over. But it turns out there's other interference models, and basically you can show that, so there's a result that says that the worst case performance of the row constraints, which is of the greedy coloring algorithm, which is determined by the induced star number of the conflict graph, that quantity is always at most 3 in a certain situation. What that means is you can never do worse than a factor of 3 in these situations. Okay. In general, this quantity can be arbitrarily large, and so the worst case performance can be arbitrarily far away from optimal. But in many contexts, this worst case performance is bounded from above by a fixed constant, and in certain and so that's what's proved here. We don't have time to go through this, but it's possible to model the interference using a hypergraph, where every hyperedge is a minimal subset of lengths that cannot be simultaneously active due to interference. So it's quite possible that you have 3 links, L1, L2, and L3, such that L1 and L2 can be simultaneously active, L2 and L3 can be simultaneously active, and L1 and L3 can be simultaneously active. But if all 3 of them are simultaneously active, the interference is too much and cannot be tolerated. In that case, those 3 subsets, which are active, they should all be allowed to be active, but the conflict graph doesn't capture that situation where any 2 of 3 links can be active, but all 3 of them cannot be active. And the 3 of them that cannot be active is a minimal set of links that cannot be active, because any proper subset of those 3 links can be active. And so any such 3 links which have that property would end up being a hyperedge. So you'll have a hyperedge containing L1, L2, and L3. Because that's one minimal subset of links that cannot be active. And you put all the minimal subsets of links that cannot be active, and you form a hypergraph. And so some of these results have been generalized to hypergraphs. My paper there is still under review, but you can look at it on arXiv or on my website if you want to look at that. So I'm going to now go here. So these are all the results on hypergraphs. We won't have time to get to that, but I want to talk about a very interesting open problem. I have 5 more minutes left, so I want to get to some open problems. So in the first part of my talk today, I gave you some results on the performance of distance de-distributed algorithms for the one-hop interference model. The primary interference model is called the one-hop interference model because in order for 2 edges in the network graph to be active at the same time, the distance between those 2 edges must be at least 1, meaning that a set of edges can be active if and only if that set of edges is a matching in the graph, right? And now you can generalize these results to the k-hop interference model. So you're given a graph G, you fix k to be at least 1, and you define a graph Lk of G, that's your conflict graph, where the vertices are the set L of links in the network graph, and 2 links, Li and Lj of the network, are adjacent vertices in Lk of G if and only if the distance in G between Li and Lj is at most k minus 1. So if you look at k equals 1, what happens? You're saying two edges in the graph G or adjacent vertices in L1 of G, if and only if the distance between them is at most 0. Well, the distance between two edges is at most 0 if and only if they have a common endpoint, right? If and only if they're incident to a common vertex. And that's why L1 of G is exactly the line graph. So under the K-hop interference model, two links can be simultaneously active if and only if the distance between the two links is at least k. So instead of saying that, so basically this is a stronger form of interference. When interference is very high, even edges which are apart by a distance of one edge, if two edges have only one edge between them, they might be a matching, but they might still interfere with each other. So in a two-hop interference model, you require any two edges which want to be active at the same time to have at least distance 2 between them. So one open problem, I want to talk about open problems, is there are many known properties of the line graph L of G, also denoted L1 of G. For example, Whitney showed that if for any two graphs on 5 or more vertices, those two graphs are isomorphic if and only if their line graphs are isomorphic. And in fact, Whitney showed that the automorphism group of the line graph of a graph is isomorphic to the automorphism group of the graph itself. There are many results that say that a graph is a line graph if and only if it does not contain one of the following 9 subgraphs as an induced subgraph. So there are these forbidden subgroup characterizations of line graphs. One can find the fractional chromatic index of a line graph in polynomial time. It turns out that it's already been shown that one can't find a maximum matching or a fractional chromatic index of Lk of G in polynomial time. So the problem of Lk of G is more difficult, but it's an open problem. I mean, certainly L2 of G, the graph constructed from G in a very particular manner shown here, has a very particular structure to it, similar to how line graphs have particular structure to it. Maybe you can show that L2 only, not all graphs can be L2 of G graphs, right? Not all graphs can be obtained in this manner. So I'm sure there exist graphs which are not L2 of Gs for any Gs. Okay, and so you can whatever results are known in the theory of line graphs could be generalized. So just a little bit more about this theory. A subset F of edges in a graph G is called a k-separated matching if the distance in G between any two edges of F is at least k. So a one-separated matching is just a matching, and a two-separated matching is called a strong matching or an induced matching. And some theory has been developed for the theory of strong matchings or induced matchings. For example, it's NP hard to compute even in very special cases. So finding a maximum size of a strong matching in a bipartite graph is NP hard. Okay. So under the K-hop interference model, a set of edges that can be simultaneously active is exactly a k-separated matching. So for example, that the edge coloring number of a graph is the minimum size of a partition of the edge set of a graph into matchings. Well, you can ask the question, what is the smallest size of a partition of the edge set of a graph into two separated matchings, which are strong matchings, or three separated matchings? You can do this. So edge coloring and its fractional variants have been well studied, but they all correspond to the k equals 1 case. So some initial results of these generalizations are available in a paper I have under review, which you can find on arXiv. Again, I'll share these slides with the organizer, but some initial results are available there, but many open problems are there. You could just look at this reference to find some of the partial results that are there, which still need to be extended.